In this video, we introduce a simple yet effective method for occlusion-robust 3D human mesh reconstruction. Our task aims to estimate skinned human mesh from a single RGB input, and there are two main streams for this task. One is the model-based method, which predicts SMPL parameters. And the other one is the model-free method, which directly infers the 3D coordinates of mesh vertices. Between these two approaches, we follow the former one, model-based method. In the field of 3D human mesh reconstruction, person-to-person occlusion is one of the most important issues. When multiple persons are overlapped in the scene, it is difficult to distinguish who owns each body part in the image. To alleviate this ambiguity driven by person-to-person occlusions, we represent the possession relationship between all human instances and their visible body joints in the feature space. Specifically, two different feature maps are encoded from the input image. One is the center-aligned instance map, which contains the identity representation vector at the center position of each human body. The other is the joint-aligned instance map, which contains the same identity representation vector as mentioned earlier, at each person's joint locations. By referring to these instance maps, the model can more easily understand the spatial occupancy of body parts for each human in the image. For example, the model can know that this elbow belongs to person A, and this elbow belongs to person B. And the owners of other body parts can be distinguished in a similar way. Now, let's take a look at the detailed learning process to represent the identity information in the instance maps, so-called instance-aware contrastive learning. First, instance maps are encoded through the convolutional network from the input image. After that, we sample center features at the body center positions of the center-aligned instance map. Similarly, joint features are also sampled at the body center positions of the joint-aligned instance map. These sampled features are projected into the latent space via MLP layers. In this latent space, we apply the push and pull mechanism of contrastive learning based on the cosine distance. Specifically, the center feature of person A pulls joint features of person A, and the center feature of person B pulls joint features of person B. At the same time, the center feature of person A and person B push out each other. By doing this, identity information can be distinctively embedded at the center and joint positions of each instance map. Now, let's see how the distribution of center and joint features changes in the latent space as training progresses. The example input image with circular color marks is shown on the left. Dark colors indicate body center positions and bright colors indicate joint positions of each person. As illustrated on the right side, feature vectors are irregularly distributed in the early stage of training. In the middle of training, the center feature and joint features corresponding to each person are gathered together, but the features of the overlapping people still do not seem to be perfectly distinct. However, after the training ends, we can see that feature clusters of each person are successfully separated in the latent space. This is the overall architecture of the proposed network, which follows the bottom-up 3D-HMR framework. When encoding instance maps, the estimated center heat map and joint heat map are utilized, and the ground truth of center position and joint position is used in the sampling process of the instance-aware contrastive learning. Note that the instance-aware contrastive learning scheme is conducted only in the training phase and eliminated during the inference. The encoded center-aligned instance map and joint-aligned instance map are incorporated into the network branch for estimating SMPL parameters by concatenation. To accurately indicate valid locations, the center heat map and the joint heat map are also employed for this process. Finally, pose and shape parameters of each person are sampled from the SMPL parameter map according to the predicted center position, which is used to reconstruct human meshes. As can be seen from the qualitative results, our method achieves robust performance under complicated person-to-person occlusions, compared to previous works. We can also see that our model has a great ability to reconstruct human meshes in crowding scenes. These are some more examples. Thank you for watching, and please visit our website for more information.